All right, can everybody see my screen?
Yes.
Awesome. So Alex, you wanted to know how you can get started without any hardware, right?
Yes, you're right.
Yeah. Today we're going to cover that as well. And we're going to talk a little bit about debugging embedded systems, but with special emphasis on kind of running things on Linux instead of running on the real hardware. So we're going to cover a little bit of emulation, and also I'm going to show you how to compile Linux as a user space application, which is actually pretty cool. So just to cover a little bit about debugging options that we have, you have basically JTAG debugging, where you connect to your actual hardware, to your board, and you use GDB to interact with the chip directly. You can pause the execution on the chip. You can inspect current program counter value, where the program is at the moment, and dump memory, dump variables, and things like that. And the way that works is that you connect to the JTAG adapter as a GDB. You start a GDB server that is connected to the JTAG adapter, and then you connect using GDB to that GDB server, and then you can interact with the hardware over the JTAG connection. But we do have other options. There is, for Linux, there is KGDB, which is debugging over serial interface, but that also requires hardware, access to actual hardware. But then we have two other options. We have debugging like a normal program, where you compile either, it doesn't matter if you're working with Linux kernel or if you're working with RTOS, you can usually compile the system for your PC and run it as a normal application. So many, like I wouldn't say all of the systems, but many of the bigger systems have build targets where you can compile the program to run as a POSIX. Like you can compile it against a POSIX target and then run it as a normal executable on your computer, and you can then use normal GDB tools to debug that executable because it behaves exactly like a normal program. And we're going to cover a little bit of that. And then there's also another option where you actually emulate the hardware. So you can use QEMU to emulate actual chip. For example, if you compile for Cortex-M3, you can emulate Cortex-M3. And there's a number of boards that are supported by QEMU, which you can use as your build targets. And that gives you really a system that behaves a lot like the real system. So here you can step through the execution at the lowest level, at the level of the scheduler, where you can actually step through the interrupt handlers and inspect how the code is working down to the lowest level. So QEMU debugging is really the most useful way if you want to have the same experience as you have when debugging on the real hardware, except that you have control over the execution of the program and you don't actually need real hardware because it's all emulated. So like if you want to learn more about KGDB, you can go to the kernel.org documentation. There is a long explanation about how to use it. It's under DevTools under the version of the kernel that you want to look at. QEMU is available on GitHub. You can compile your own QEMU with whatever options you want to enable. There's it supports many different architectures, so it often makes sense to compile your own QEMU. So you'll find it on GitHub, on the official GitHub page, QEMU/QEMU, and there is a GDB debugger. So we're going to be using GDB to connect to the hardware and to debug it. So let's start with a little unusual thing. I don't know how many people on the call here know what user mode Linux is. Does anybody know what user mode Linux is? Have you ever built a kernel for user mode Linux as a target? So nobody built user mode Linux before.
No, me not at all.
Yeah. So user mode Linux is an interesting build target for Linux, which allows you to build Linux, the Linux kernel itself, to build it as an executable. So when you configure Linux kernel as architecture you build Linux kernel into an ELF executable. So basically a program that you can start and run as your normal user. You don't need to have root access to run this program, but it behaves just like the real kernel. So you can supply a RootFS image to it with all the programs, with all the applications, and you can use this system as a virtual system, but it runs completely as a user mode application. So you're basically compiling the kernel, the full kernel, and then you call it from your shell as just a normal application. So basically Linux, and then you supply rootfs type. If you use hostfs is very useful because it gives you access to your directories of the host system. So you don't need to have a rootfs image to use user mode Linux. You can just use it with your native hostfs that you're using on your computer, but it's going to be an isolated system. So it's kind of like in between a Docker container and KVM. So it's a little bit more isolated than Docker container, but it's not the same as KVM because it's not using virtualized hardware. It's using just a virtualized access layer to the system calls on Linux, and a little bit more besides that. But it's pretty much using like an interface from user mode into the main system. So you can then call Linux and just supply hostfs and supply an init program, and you get a bash shell basically running in this virtual environment. Now, if you're using hostfs, you obviously have access to all the host files, but you don't need to use hostfs. You can use a separate image with a rootfs where you would have a completely isolated environment. And you can even have a directory that where you put your rootfs for the user mode Linux application, and then you can supply that directory, and it will only have access to that directory. So there's a number of options that you can set. You can check out the full list of options that you can pass to the kernel to understand kind of what you have available to you. But this is a cool way to really build the Linux kernel and test things, and not have to have any hardware to run it on, and you don't have to risk bricking your own system, because you can run it as a user application. You don't need to reboot or or do any or set up any emulation or anything like that. This is the simplest way to really just build the Linux kernel and then use it. So so how do we actually debug the kernel then if we are compiling this user mode Linux executable? Well, we can start the user mode Linux, and we'll get a shell. So we run our init program, and then we can just connect to it using GDB. So we can start the program first. We can then list all the processes that we have running and find the process ID of this of the Linux that is running, and we can then just connect to it from GDB. This is a better way because by this time you have already started the system, and you can then just set breakpoints on, for example, system calls, and you can trap or tap into the entry points, which you can then trigger from a user space application, for example. So one example is, for example, if you set a breakpoint on write call. So if you call b cases write, that's going to set a breakpoint on the system call for write. And write system call is used on any file whenever an application wants to write into that file. And this also includes the terminal itself. So if you press a character on the terminal, the bash shell that is running on the terminal is going to then echo that character back, and that is done using the write call. So if you put a breakpoint on casus write and you just press a key in this terminal that you have from the Linux that is running, you will then get a breakpoint in the write call, and then you can step through the application itself. So this is a neat way to quickly get started and quickly get into experimentation with Linux kernel without having to have any hardware, without having to understand how an emulator works. This is exactly, the development process here is exactly the same as you would have with any other application. So this is like any other application that you develop on a Linux system. You can debug the Linux kernel itself in exactly the same way. So this is kind of like Linux built to run on Linux, which is kind of neat. But that's the Unix philosophy, right? So we have compilers that compile themselves. We have kernels that run on themselves and things like that. So it's really cool. This is one option. If you want to run a RootFS, you can build your own RootFS. There is different options for building your own your full file system. So the smallest option you have available is BuildRoot. BuildRoot is actually used to build firmware for smaller boards, embedded systems, and digital boards. So BuildRoot will build even the Linux kernel itself, but also the user space applications that are needed to be able to use the system. But you can use it to build a RootFS separately. So one workflow to develop smaller Linux systems is to actually build the kernel separately and build the RootFS separately. So you put the RootFS on an SD card, and you have your Linux kernel on a separate partition on that SD card. And when you recompile the kernel, you just copy the kernel itself. And when you need to install an application, you can just cross-compile that application, move it to the RootFS, or you compile the whole RootFS and you just copy the files that have changed, right? So it's kind of a way to incrementally just test things when developing. So you can have you can build the kernel and the RootFS separately. And RootFS contains all the applications. So all the applications that you have on your system, like for listing files, ls or echo or bash itself, the actual terminal shell, all of those applications are part of the RootFS. So RootFS is just like this full minimal file system that you need in order to be able to use any applications on your embedded system. So you have a number of options for building a RootFS. There is BuildRoot, there is OpenWRT. OpenWRT's BuildRoot is geared towards very small systems. OpenWRT is geared towards routers. So OpenWRT has very good networking support and support for like things like video streaming, anything basically that that is specific to broadband modems. So OpenWRT is centered around broadband modems. That's kind of their niche. And most likely the broadband modem that you're using today in your house is running OpenWRT. Like most probably it does, because there's millions of modems today using OpenWRT as their base system. There's also Yocto, which is a slightly bigger system. So it takes much longer time to compile. And there's Debian that you can run on Raspberry Pi, and it's the biggest one. So if you're going to build a Debian system from scratch, it's going to take a few hours to build that. If you build a BuildRoot system from scratch, it takes maybe half an hour to build a full system, depending on how fast computer you have. So BuildRoot is definitely the simplest one to really build a whole system from source code. So you're not just building the kernel itself, you're building the whole system from source code. And you can then use this RootFS with your user mode Linux to actually have a system that runs as a user process. So you don't need to have any hardware. You can build a full system with an image, with a file system image, and run it as a user space application. So that's really cool as a way of getting started and getting into the understanding the source code, how it's laid out, how to use the tools, how to connect and inspect the running program using GDB, for example, and things like that. So you don't need any hardware to do that either. Now, another option that you can use is to actually build for an emulated system. So this works for microcontrollers as well as microprocessors. So there's a number of systems that are supported by QEMU. It's a rather limited list. It's a large list, but it's still limited. So it's when you use a QEMU emulation, you're basically emulating the chip itself. So you're running the actual code that you have built for an ARM microcontroller. Like let's say you're using STM32 microcontroller. That is a Cortex-M microcontroller. So you can build code for Cortex-M microcontroller, and it's going to be ARM code, and it's going to run exactly the same on QEMU as it does on a microcontroller. So when you're using QEMU, you have the option of starting the system and then also instructing QEMU to start a GDB server. So when it comes to embedded debugging, in an application, if you're developing a user space application, you don't need to have GDB server because you're just debugging things directly. But if you are debugging an embedded application, then the way it typically works is that you have a GDB server. And this is an instance of GDB, or this is a GDB server to which GDB then connects and can inspect the CPU registers and all the details of the hardware and give you the, and display that to you as a user, right? So when it comes to QEMU, this is no exception. You can, it has GDB support, and you can start a GDB server from QEMU, and then you can connect to that server. So you use an option /s, a small s, and then a big S instructs QEMU to start the kernel, but to not run it. So it's the big S means stop, and the little s means the same thing as GDB. And then if you supply an option / or -GDB, and then TCP, and then a port on which it's going to be listening, that's there is a shorthand option which is just -s, which is basically the same thing. But if you want to figure out how different systems or different make scripts run QEMU, you can supply verbose =1 to any make process, and it will just dump all the commands that it's running. So that's a useful way to do that. I've done that here for a Zephyr build for Cortex-M, and there's a handful of more options. But if you just run make debug server for a Zephyr application, it's going to start this debug server for you. So you don't need to remember this long command. You can just build an application and just start a debug server. So if you build your application for QEMU Cortex M3 as your target when you're working with Zephyr, you can then just call make debug server, and it will start a GDB server through QEMU, to which you can then connect. And how do you connect to this GDB server? Well, you can't just use your normal GDB to do that, because your normal GDB probably doesn't support ARM by default. So there is a separate package for debugging embedded applications, which supports more architectures. And traditionally, it was a separate GDB for every type of architecture, but now we have something called GDB multi-arc, which supports multiple applications or multiple architectures. And you can then connect to the GDB server that has been started through QEMU by calling GDB multi-arc and supply the ELF, or the executable file from which it's going to read the symbols. So how this works under the hood is kind of like you have the GDB server running. It runs the actual code. It has access to the QEMU internals that run or emulate the actual code. And the GDB then connects to a socket to access those internals inside QEMU. And you pass the executable to GDB just for the sake of reading symbols. So in order for GDB to know which function you're in right now and show you the source code that is currently running, it needs to be able to read that from a program file. So the file that you supply to GDB, it's not the program that's going to run, it's just a program that you're debugging, so that when GDB reads the current program counter from the hardware or from QEMU, it can then know where the program is right now in source code, and what symbol you're currently, what function you're currently executing in. So that information is stored in the executable file itself if you compile it with debugging options. So -G is for compilation with debugging options, but that would depend obviously on the compiler you're using. When you then when you then run a command in GDB target remote and you supply the port to which to connect, it's going to connect to the GDB server, which you have started from QEMU, and then you can debug your application that way. And in this case, you can debug down to the interrupt level. So you can set breakpoints on interrupt handlers because you're basically compiling the same code that you would run on the microcontroller, but you're compiling it to be run on QEMU. And that's really kind of the closest you get to hardware without actually having real hardware. So what are the problems and challenges with this? Well, the biggest problem is that you don't have really good support for exotic hardware on emulation. And even if you're compiling for a POSIX target, you have to think about that from the beginning of the project. It's really hard to implement this portability later in the project. So if you've started a project, a bare metal project, and you don't have the user space application target, a build target for compiling your code to be run on as a user space application, then you're going to have trouble because you're going to have to change a lot of things in your code and restructure it to be able to compile your application for a user space target, or even for QEMU targets. So it's important to start early in the project and to implement that early so that you don't have to then restructure the code later, because that's going to take a lot more effort to accomplish later than if you start from the beginning. And for example, hardware that you might have some LED controller or some Ethernet controller. So there can be hardware on the board that you will use to run your application on that is not easily emulatable in QEMU. And even more so, if you're compiling as a user space application, you basically need to find a way to emulate things in the user space application and to be able to run your program and test its behavior, but without having to actually implement every little detail of the emulation. So what you would do then is try to emulate behaviors instead of emulating the hardware. So if you have a LED controller, you would not emulate the I2C level transactions for that LED controller. You would just emulate the behavior of the LED controller. So part of the, like if you're running on as a user space application, you would just not have that lowest level that communicates with hardware. You would just have behavioral simulation. So you could set up, for example, a shared memory region where you can store the state of the program, the state of the LEDs. If you have some LED or some other type of display, you can store the state of that display as a shared memory in a shared memory region. And then you can have a GUI application that runs on Linux that reads that shared memory and displays the state for you in a more accessible way. So that's the limitations of basically of emulating things and not having the actual hardware. So obviously the best method is to have the actual hardware and to debug it over JTAG, because that gives you maximum flexibility. You're actually running on the chip, and you can step the program on the chip. So all the details of the program state is fully accessible to you as it is accessible to the chip. So you're seeing the same things. If you're doing emulation, you would have to cut things down a little bit and focus on the higher level logic of the application instead. So that's it for today, and let's have a discussion now about debugging and about the topic that we have here. So I'm most interested, I think, to hear from Alex. How do you, was this useful to you, Alex?
Yes, that's very useful and interesting.
Okay, awesome.